Cool. Did you have a test yesterday? I thought there was quite a lot going on the group chat with people terribly stressed and what module was it? BI302. Oh, that's the cell biology stuff and things like that. And it was a noodle test, wasn't it? How do you go? Okay. It was all right.
I mean, nice where it was, I say partially open, but if we really weren't sure.
But, so that was multiple guess. Yeah. Mm. Oh yeah. How big is a human cell? 10 miles? 1 meter?
They were a little bit smaller range than that.
Okay, yeah. I can see that.
I saw on our deadline table thing that we have a test for skills for biosciences, but I'm not sure if because obviously some formulas are included. Are we going to be given them, or do we have to remember them?
The equations for which test are you talking about?
I think it says we have one in mid-November, either 11th or 14th or something like that.
Do you mean the SS practical?
Not a practical, it just says test. I think it was online. I can check right now.
For my module,
yeah.
You have a test, I think, an in-class test in week 12.
Oh, okay.
That is shortly before Christmas. It's the last week before Christmas.
It's probably the 12th or the 6th of December then?
Yes.
Okay.
Yes, that's right. Will you be given any equations? No, you won't, because this test will be open book.
Oh.
It will be a problem-solving test, and it's open book. You can use whatever resources you deem necessary.
Are you allowed with your own notes, or does it have
Absolutely.
to be?
The only thing that you can't do is access the internet.
Okay, makes sense.
Yeah? Or phone a friend, or have somebody else do the test for you. All right, most wonderful good morning, ladies and jelly beans. session 1 out of 3 today. You are so lucky, right? Getting me for 3 hours. A lot of people would pay a lot of money for that if they could. I've just been asked about the test that we are going to have next week, the in-class test. Yes, I still can do it. Yes, I can still troll you. Ah, fantastic. No, don't worry, there's no in-class test. There's the assessed practical next week, which is, of course, open book, as I told, the week after, sorry. Okay, there's the assessed practical in week 8. You can bring whatever resources you deem necessary for that. You can print out practical manuals until you are blue in the face. The instructions that you will get from me, or you've already received the instructions from me, for the assessed practical, but actually I should say I should make this announcement later in the lecture when all people are there. So okay, let's just forget that. Let's focus on logarithms for a while. Is this actually done in A level in your syllabus, logarithms? So you should all be familiar with logarithms, right? No? Oh, only in A-level maths, not GCSE. I see. Okay, good. Now that can cause a little bit of controversy. Sorry? It's only natural log. Ah, so you haven't done log to the basis of 10. Yeah. Okay, so logarithms are incredibly useful if you are dealing with huge numbers or with with large orders of magnitude. So, for example, if you ever wanted to visualize the size of things from, let's say, from an atom to the size of the universe, you would have a massive scale from basically 10 to the 9 meters, or 10 to the 10 to the minus 10 meters for an atom, to the size of the universe, which is about 10 to the God knows what meters. And if you wanted to put that all in one scale, you would really struggle with that. But logarithms basically make life much easier because, well, you can condense things with it. And the way I like to think about logarithms is just by simply using a simple equation which reads like 10 to the power of 2 equals 100. Looks totally basic, absolutely, I fully agree. But what you can do is you can identify this 10, that is our base. The 2, of course, is the exponent. And the 100, that's the value. And what you can do actually is you can convert that into a log equation, a logarithmic equation. And you can basically write this as log to the base of 10 of 100 equals 2. That is basically the concept. With a log, you find the exponent of something. And in this case, of course, it is absolutely trivial. But what if you have a scenario of 10 to the power of 1.477 equals x equals, no, actually I should write that in a slightly different format. 10 to the power of x equals, let's say, 5. So this is something where you would say, that's a bit weird. I know that 10 to the power of 1 gives me 10, so x is probably smaller than 1, but exactly what is x? Right? What the heck is x? And with this equation here, you can figure it out what is x. So you can write this equation, this one here, in order to figure out. You can write this as log to the basis of 10 of 5 equals x. And that allows you then to use your calculator and just simply do that. And in general, you can do that not just to the basis of to the base of 10, you can do that to whatever number you can think of. Yeah? For our purposes, for the BI308 module, we will only encounter two different bases. We will only encounter the base 10 and you've encountered that for any kind of pH calculations. And the other base that we encounter is a really weird number. It's, I would say, my favorite number. It's 2.718, and then it has an infinite number of digits. And this 2.718, you might say, this is a really weird basis. Where the heck is this coming from? Well, actually, this is one of the most famous numbers in the history of maths. This is also called E. And it's abbreviated with a lowercase e in honor of the famous German mathematician Euler, which is spelled with an E. And we will come back to where this E actually comes from when we talk about first order kinetics, so let's not worry about it. Now, coming back to this log 10 of 5 equals x, usually I'm just simply too lazy to write the subscript 10, so when I write log, you know it's to the basis of 10, right? That's sort of a convention. People don't write the 10 and just simply write log, then it means log to the basis of 10. So log 5 equals x. Let's just quickly check out what is our x. So I've got a calculator here. Log 5 equals 0.69897 something. Let's just simply round that to 0.7. So in our case here, x equals 0.7. So we can say 10 to the power of 0.7 is roughly 5. Okay? That makes sense. And if you sort of remember this bit here that I've done here with this really basic 10 to the power of 2 equals 100, and you really can't really go wrong with applying the rules of logarithms. Now, what are the rules of logarithms? There are a few rules which you obviously need to remember, and in fact, I would say, while I've got 5 rules here, you only need to remember 3 of them. It's the product rule, so if you have a multiplication inside your bracket before you do the log thing, you can also split that up as a sum of the individual logs. So you've got here the sum of the individual logs, log, and this a can be any base, it doesn't matter what it is. It is true for any base. So say log 10 of x plus log 10 of y can be written as log 10 of x times y. That's quite an important rule which you will encounter quite frequently. The quotient rule, or ratio rule, you need to remember this guy here, where you can write a ratio x over y as log x minus log y. And again, the base doesn't matter. And last but not least, the power rule. If you've got something to the power, then you can get the power, the exponent, out, and it is simply a multiplication. The change of base rule, to be frank, whenever I encounter it, I have to look it up, because I don't use it very often. It's quite useful sometimes, but for our intent and purposes, we don't really need that. And the equality rule, again, is just sort of, something for the mathematical connoisseurs. If you really don't have anything else to worry about in life, then you learn the equality rule, which is basically rather trivial anyway. Okay, now I've put something down here, but before we get into it, I would like to sort of give you a sort of a hint or a trick, because if we've got, for example, something like 10 to the power of x equals 5, and we want to find out this x, what this x actually is, what is the formal procedure for doing that? So how can we get to this x? What do we need to do? Now we know that from the previous session about maths, we know that if we've got, for example, x minus 5 equals 8, in order to get this x, we want x on one side. We want to remove the 5. So what we need to do in this case is we have a negative 5. So what we do is we use the inverse mathematical operation of minus. We add to both sides 5 plus 5. It's the inverse mathematical operation. And we get x minus 5 plus 5 equals 8 plus 5. And you see, minus 5 plus 5, they sort of cancel each other out. And we have got x equals 8 plus 5, which of course gives us 13. So that's the introduction of the inverse mathematical operation that we can use. And with logarithms, we can do exactly the same. If we've got 10 to the power of x equals 5, what we can do is we can use the inverse mathematical operation of 10 to the power. So the inverse operation of 10 to the power, and I abbreviate it like that, 10 to the power, the inverse operation is log 10. Note, we have got 10 to the power and log 10. And what we do with this is we basically take both sides, and it has to be both sides. Both sides we take log 10. So on the left-hand side, we get log 10 of 10 to the power of x. I'll put that in brackets. Equals log 10 of 5. So that's sort of the long way. And the reason I've done that is because we know that log 10 and 10 to the power eliminate each other. They cancel each other out. So log 10 and 10 cancel each other out. So all I have left on the left-hand side is x. X equals log 10 of 5. And that is what I wanted. That's my x that I get here. Make sense? Yeah? Likewise, if you have log x equals minus 2, we want to find x. What we need to do is we need to say, all right, we want to have the x by itself. So we need to use the inverse operation of log. And I told you that 10 to the power is the inverse operation. No. Log is the inverse operation of 10 to the power. So therefore, 10 to the power is the inverse operation of log. Yeah? So what we can do is we just simply, and I probably should, be nice. I should say, here, the inverse operation is 10 to the power. So we have 10 to the power of log 10 of x equals 10 to the power of minus 2. And again, I need to do it for both sides of the equation. Ten to the power and log 10 cancel each other out, and all I have left here is on the left-hand side is x equals 10 to the minus 2 equals 0.01. It's the same as 1 over 10 to the power of 2, 1 over 100, 0.01. Okay, happy with that? Fantastic. Now, I told you that we have log 10 and 10 to the power of. We also have, as the inverse, we also have e, that's this 2.718, to the power of. So that's our base, e, base. Somebody wrote in an exam paper, it's home base. No, that used to be the DIY retailer, home base, which went bust last year. Has nothing to do with DIY. So it's E, and here the corresponding log is usually abbreviated with ln. That's the natural log. And again, your calculator should have a button for that, so that you don't have to put in this 2.718 all the time. Okay, now let's see if we can do a little bit of calculation for that. Here is an equation for you, and I basically want you to try and figure out, come up with a strategy how we can solve this. So we have 10 equals 100 times e to the power of minus k times 10. Sorry, I just had something. There's a nose pick on the screen. Okay, so question, what is k? The reason why I didn't use x is because I have a times in it and I don't want people to get confused. What is k? How can we actually do that? Well, first of all, the easiest way of dealing with that is, let's get everything that is not involved in logarithm or in exponents to one side and everything else to the other side. So we have 10 equals 100 times this e. So the ideal way would be we divide both sides by 100, and therefore I get 10 over 100 equals 100 over 100 times e to the power of minus k times 10. Again, that's the long version. I would not necessarily request you to write that down in a test or something like that. However, what you see is that we can get rid of the 100 and 100. They cancel each other out. We don't have to worry about them. And we can therefore write e to the power of minus k times 10 equals 10 over 100. And now I need to get rid of the e. And I told you how we can do that. We just simply use the inverse operation of e for both sides of the equation. So we ln both sides. Remember, inverse of e is ln, the natural logarithm. What do we get? We get ln of e to the power of minus k times 10. That's on the right-hand side, or on the left-hand side from you. Equals ln of 10 over 100. What does that give us? Well, ln and e cancel each other out. And all we have left on the left-hand side is, loud? Minus, you're absolutely right. Let's write it exactly as you said. It's probably nicer. It's minus 10k equals ln of 10 over 100. We could, if we so wish, write ln 10 over 100. We can write that in a slightly different format. How could we write that?
0.1.
We could write that as 0.1. Yeah, we could write this as ln of 0.1. We can also write that according to the rules of logarithm. We could write this as ln 10 minus ln 100. Remember the rule of a quotient or a ratio where you can take it apart. In our case, it doesn't really give us anything. So I just simply stick to this ln 0.1 or ln 10 over 100. So we've got minus 10k equals ln of 0.1. And now what do I need to do next? Well, I'm looking for k, so I divide both sides of the equation by minus 10. This gives me minus 10k divided by minus 10 equals ln 0.1 divided by minus 10. You always have to do it on both sides. Minus 10 and minus 10 cancels out. I've got k equals ln 0.1 over negative 10. If you get to that point in an exam or something like that, you would probably get 90% of the marks. Now let's do that. Let's hack that into a calculator. And it's really good practice if you do that yourself. So we have ln of 0.1 divided by negative 10. And that gives us, let me quickly do that in my head, 0.23 something. Is that right? Ha! I'm good. K equals 0.23. We'll just leave it like that. Yeah? You got the principle with LNs and E? Let's do another one. Let's say we have ln 5 over b equals -1. Now I want you to apply what you just learned. I want you to try and figure out what is b. And by the way, these are typical examples for calculations that we will encounter in week 8, the week after next. That is when we start to use these types of calculations. So I give you about 2 minutes or so. Please feel free to have a chat with the people sitting around you, come up with some strategies how you could solve this. Got it?
Yeah, I think.
Yep.
So, no. I don't think.
You do it the really hard way.
Oh, I do.
I show you
Okay.
an easier way. Okay?
Yeah. Thank you.
Good point. What do I do with the 5? They're in the way, and they're in the wrong position, aren't they? Yeah. Okay, let's quickly do it together. We could, of course, take this apart. We could write ln 5 minus ln b. And that would be an absolutely valid approach. Or the alternative is we could try and get rid of the ln first, in the first step, because that makes life much easier. So how do we do that? Let me write that down again. ln 5 over b equals -1. Now the inverse operation of ln is what? E to the power of. So I do e to the power of ln 5 over b equals e to the power of -1. Yeah? And I have to do it with both sides. My e and the ln cancel each other out. And what I've got left is 5 over b equals e to the power of -1. You got that? Well, with that, you basically have paid already 80% of the rent, because now you can very easily solve that for b. You can bring b to that side and e to the minus 1 to that side. So we multiply with both sides with b, and we divide by e to the minus 1. And what we get is b equals, did I make a mistake here? No. B equals 5 over e to the minus 1. Yeah. That makes sense? Now let's see what this is. Let's do that in the calculator. We have 5 divided by e, and I've got this e to the power of x here on my calculator, e to the power of x, and very often your calculator will show that as exp, exponent. Why it does that, I don't know, but you know, to the power of minus 1. And we get 13.6. Did you get that? Was that your? Yep. Pretty much. You did it slightly more complicated when you dissect what's in the bracket of the ln, but it gives you exactly the same result. So b equals 13.6. You happy with that? Did you get that when you tried it? Yeah, fantastic. Right, what else have we got? Oh yeah, that's a cool one. 6.5 equals 7.2 minus log r. And this log here is log to the base of 10. And the question is, what is r? Actually, you will come across this calculation in about 2.5 hours again. You want to try? Got your result?
It's just changing these places. Is it right? 6.5, 7.2 minus 6.5. Then we move this to here.
Okay, I'll show you. Okay? Now, that, again, you know, this is something that I really want you to be totally comfortable with, because you can bet that this will come up in a test at an exam. Okay, so how are we going to deal with that? First of all, let's get everything with log to one side and everything that does not involve log to the other side. And call me a traditionalist, call me a weirdo, is what my kids do. My wife thinks I'm not center of the dial. That's fine, but I like things neat and ideally without any negativity. So what I propose is we bring the log r to the left-hand side. We just simply add to both sides log r. And everything that is not log to the right-hand side. So we get log r equals 7.2 minus 6.5. Are you happy with that? Yeah? Pretty straightforward. And as you probably noticed, I'm just simply too lazy to write the 10 because it goes, if there's no base, it is 10. Okay, let's see what this is. Log r equals 7.2 minus 6.5. That gives us 0.7. So log r equals 0.7. I want to get rid of the log. What do I need to do? Inverse mathematical operation. It's log 10, so I need to do 10 to the power of, and I get 10 to the power of log r equals 10 to the power of 0.7. 10 and log 10 cancel out. I've got on my right-hand side, on my left-hand side, I have r equals 10 to the power of, 10 to the power of 0.7. And if you put that in your calculator, this gives you roughly 5. Is that right? Give or take a little bit. Let's check if my memory works. We have 10 to the power of 0.7 equals 5.01. So 5. Okay, happy with that? Richard goes thumbs up, so that means no problem. Shall we do another one? Yeah, let's do another one, just for practice purposes. 6 equals 0.5 times 8 minus log c. What is c? Basically, this contains everything that we have done so far. Shall I quickly do it together? No, you do it. So first of all, we need to recognize that it is, at its heart, it's a multiplication. It's 0.5 times something. So what we can do is we divide both sides of the equation by 0.5. This gives us 6 divided by 0.5 equals 0.5 over 0.5 times 8 minus log c. The 0.5 cancels out, and on the left-hand side I've got 6 divided by 0.5, and if I'm correct, then this is 12. Is that right?
Yeah.
Thank you. 12 equals 8 minus log c. That's what I've got left now. Now all I need to do is really do what I've done in the previous example. I bring the log to this side, the 12 to the other side, and I've got log c equals 8 minus 12, and that equals minus 4. So I've got log c equals negative 4. Now in order to get rid of the log, and again it's base 10, I use the inverse mathematical operation. So 10 to the power of, I've got 10 to the power of log c equals 10 to the power of minus 4. 10 and log cancel out, and all I've got left is c equals 10 to the minus 4. Simples. I'm a victim of advertising. Does that make sense? May I suggest to you that you do a little bit of practice questions on my wonderful practice calculation website in your own time. And otherwise, I also suggest that we have lunch and then meet again at 2 o'clock, where I will go through the practicals that you do next week and the week after. See you later. Thank you very much.